So it's a very beautiful day. The weather is so fine, but we need to study computer architecture, even though the weather is so good. Okay, so before starting today's class, so I will share the Piazza. Okay. So can you see Piazza? It's a Piazza website. So you can find that many questions are being posted on Piazza. So it's very good. So TAs and I try to answer the questions very quickly. So if you have any questions, and then please post your questions on the Piazza. So it's a very good tool. Also on the resource tab. So I posted solutions for homework assignment number 1. So you can check the answers. So then the TAs are grading the first homework. So I think you will get the grading result soon. So, and then also I posted the first lab assignment on the Blackboard. So actually the last week. So this this lab assignment is just installing the Verilog simulation tool called ModelSim, and then try to create a very simple module like AND, OR, and subtractor module, and then try to simulate your module with the test bench. So that's the purpose of the first lab assignment. So this is just a it's a very similar to the preparation of the following design labs. And if you are not familiar with the Verilog design, then you can find several resources, materials here. So here you can find the system Verilog tutorial. So system Verilog is a little bit different from normal Verilog. Actually, it's easier than Verilog because so we don't need to use the rag or wire for the system Verilog. We can use just the signal. Also, if you are not familiar with the Verilog design or test bench design, then you can read these slides like Verilog test bench design and the Verilog design slides. Also, you can find the document that compare system Verilog and Verilog. Even though you are familiar with the Verilog, then you may not be familiar with the system Verilog because it's a somewhat so more modern tool, so modern language. So you may not be familiar with the system Verilog, but you can just compare the system Verilog and versus Verilog by reading this document. Okay. So and then if you did not take the digital logic design course, then try to study the digital logic design by yourself. So okay, so actually some knowledge will be required to design the pipeline, the processor, or some very simple single cycle processors. So the lab assignment of 3 and 4 will be it's a little bit more difficult than more difficult than the first lab assignment. Okay, so try to be prepared for the coming lab assignment. Okay, let's go back to the slide. So in the previous class, we learned about the procedure or function call. And then in order to support this procedure or function call, RISC-V also provide jump instructions. So it's an unconditional jump. So actually we learned about the conditional jump So conditional jump means that if the condition of this conditional jump instruction is true, then the PC is changed to the target instruction. So that means that the assembly code jump to the target label. Okay. But what is the unconditional jump? It's just a jump to the target location of the program. So now to support the function call. So someone posed the question about the function call. So function is the terminology of high level language, right? So if you use a C, so actually if you create a very simple C program, then you need to make main function. So it's also function. So that means that this function is called and the statement. So it's actually it's a statement means that it's like an instruction. So statement inside of a function is executed. Okay, so that's why I use the instructions or statement when I mention a C program. Okay. So actually, in a C program, the main function is the code. This is just a main function. Okay. And then also we can find the additional function inside of this main function. So this is also function call. And now to support the function call, actually function is called regardless of the condition, because okay. So the function is just a group of instructions. So that means that if a function is called, then the assembly code need to jump to the target location. And then this target location will be the first instruction of a function, okay, of the target function. So if the function is called, the instructions inside of a function is executed, and then if function completes its own execution, then the program returns to the parent function. Okay, so the parent function, so main function, so it's in this example, the main function is a parent function, and then this full function is just a function, okay, or a procedure. So it is called the subroutines. So in order to support the function call, RISC-V provides the JAL, so it's the jump and link, and then JALR is jump and link register. So we can use JAL when the function is called, and then we can use JALR when the program returns from a function. Okay. So if the return is called, like in the C program, we frequently use return statement. So return means that the program returns from this function. Okay. So if the return is executed, then actually this return is translated into the JALR. Okay. So, so we also learned the example of the leap procedure example, and then also we learned the non-leap procedure. It's a recursive function. So also one student asked about this function. So actually, so in this slide, it should be 1, not F. So it is a typo. So it should be 1, not F. So yeah, one student found this typo. It's a very good student. It's okay. So also try to, so this is the very familiar function because it's a recursive function, and then this function will implement the factorial. So we already know, I believe every student already knows about the factorial. So that means that when this function is called, if the n is bigger than 1, then this function call its own function. But what is different? The argument is changed. So arguments are the input data of function. So this just the arguments are changed, and then the function is called again and again. And then we already learned that when the function is called, then the function is just a new group of instructions. So and then the function is called the data. The register data used by parent function should be stored in the temporary memory, temporary storage space. And then this temporary storage space is called stack. Okay, stack. Oh my. And then, so it's also the same when for the recursive function, it's a non-leaf function. So when the function is called, the stack pointer is adjusted, and then so that means that the space for stack memory is assigned. Then the function stores the register data inside of this stack memory. Okay, and then the function instructions are executed, and then when the return is executed, then we can use the JALR here. So try to understand this recursive function, okay? The assembly code of a recursive function. It's very important. Okay. So also, so actually we will learn about how the binary program is executed in the computer systems. So actually when the execution file is called the binary file, it's just a group of assembly instructions. Actually, the assembly instructions are one-to-one mapped to the machine instructions. So when the binary file is executed, then these instructions are just executed. But we already learned that the instructions are also data. So when the binary files are executed, then operating system like Windows or Linux operating system assign a memory space. So memory space. Okay. So but this memory space is just a virtual memory space, not it's a, so we will learn about the virtual memory later, but just here. So it's actually the operating system assigned virtual memory space to its execution file, and then the data used by this binary file is stored in this virtual memory space. So okay, so this is text data. Text data is the instructions, and then static data. So we can just in a C program, you can just declare the static data like with the static. So this data is also stored in this virtual memory space, and then the data can be allocated dynamically with the malloc function, or in the Java we can use the new function, so new or malloc. So when the dynamic data is created, then this dynamic data is also stored in the upper space of the static data region. Okay, and then the dynamic data increases to the upper direction, and then stack is the temporary data. So the stack increases to the lower direction. So okay, so I believe someone knows about the Stack Overflow. This is very famous site for programmers. So if you have any problems, you can ask questions on the Stack Overflow. So actually, the Stack Overflow means that the stack space means this dynamic data memory space. So stack is overflow to this dynamic data region. So that means a stack overflow. That is a kind of a program bug. So it's called the stack overflow. Okay. Okay. So now we will learn about how the additional instructions of RISC-V and then how the programs are compiled and executed in the computer system. Also, we will cover some information about the instruction set architecture of x86. It's a very popular instruction set architecture. Okay. So if you are very cautious, then you can find, so this is the register name. So usually we use this register numbers because the RISC-V supports the 32 general purpose registers. But we can find that some registers can be translated into the ABI name. It's the some specified name because the compilers use a certain registers as specific purpose. So for example, usually, so just a recommendation, but usually the compiler keeps these register usage low. Okay. So compiler use X1 register as return address of a function. So that means that instead of X1, you can use the array. Okay. You can use SP, the stack pointer is the actually X2. So blah 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 blah. So you can find that this is the FP. That means the frame pointer. So you can find the FP here. So this is called the frame pointer, and then frame pointer just indicate the start point of current stack memory. So what does that mean? So we learned that stack pointer grows to the lower direction of the memory space. So that means that when the function is called, stack memory the stack pointer is decreased. So I frequently use the pointer, but you can understand that pointer is actually address. It's a memory address. Okay, so I frequently use pointer. Actually, it's a concept of the C program. Okay, but we frequently use the pointer also. Okay, so many programmers use terminology pointer. Okay, so stack pointer grows lower direction, and then frame pointer just indicates the start address of stack memory. So if the new function is called, then frame pointer is moved to the first address of this new stack memory, and then if the new function is called, so stack pointer is adjusted, and then some register data is stored in the stack memory. Okay, but in the stack memory, so it's a temporary space. So actually, the local variables and then some temporary data used by local function can be also stored in this stack memory. Because so just remember that the RISC-V has only 32 general purpose registers, and then actually we use such registers for some different purpose. So actually the number of general purpose registers is smaller than 32. So, but sometimes the function may use the more data, okay, large amount of data. Then this temporary data also stored in the stack memory. So in the case, the stack pointer need to be adjusted also to the lower direction. So the frame pointer just points the first address of this stack memory, the current stack memory, and then we the instruction actually the function that means the instructions inside of a function just adjust this stack pointer, and then the program returned from this function, then frame pointer returns to the previous address, and then stack pointer is also restored. Okay, so sometimes, but we don't need to use this frame pointer always. Okay, so sometimes some compilers use this frame pointer. So as you can see, you can use the frame pointer if required. So this x86 is shared to the saved register and frame pointer. Okay, sometimes it is used. It's not an important concept. Okay. Okay, let's see another some additional instructions of RISC-V. So let's okay. Okay, so let's see the additional instruction of RISC-V. So we learned that the RISC-V instructions handle immediate data. So that is so I-type instructions handles the immediate operands. And what is the size of this immediate operands? It's 12-bit, and it's 2's complement. So that means we can use the minus number. So it's a negative number actually. We can use the negative number for the immediate data. So that's why we just have the RISC-V just has add I, not sub I, because with this add I instruction we can use the minus value. So it's a negative number. But sometimes this 12-bit immediate data may not be sufficient. So that means that we may use the very large number, right? So actually, so with this 12-bit 2's complement number, we can just handle the -2 to 11 to 11 minus 1. Okay. So, but if we just handle the very large number, then we need to use the more bits for this number. So how can we use this large constant number? And for this purpose, RISC-V supports the LUI instruction. So this LUI instruction has the destination register and just constant value. So with this constant value supports the 12-bit immediate value. So, but this constant value just stored in this destination register from 31 to 12. Okay, 31 to 12 like this. So if this instruction is executed LUI X19 and 976, so then this immediate number is stored in the bin number 31 to bin number 12 of the register file, the destination register file X19. Then how can we fill the lower part of this very large constant number? So we can use the add I instruction. So with this add I instruction, we can fill the lower part of 32-bit constant number. Okay. So in order to fill the just 32-bit constant number inside of a register file, we need to use the two instructions like LUI and add-I instruction. Okay. And okay, also let's see the structure of a branch instruction. So this is the structure of the format of the branch instruction. So this format is called the SB format. So as you can see, what is the branch instruction like BQ, X1, X2, and label? So actually the label is the program counter of the target instruction. So actually is the immediate number, immediate operands, and then X1 and X2 are source registers. So with this conditional branch instructions, this instruction requires two source registers and one immediate operand, and that's it. So it's very similar to add-I instruction. So, but add-I instruction requires one destination and one source registers, but it's a little bit different, but actually BQ, like the conditional branch, requires two register numbers and then one immediate value. So how can we organize this data? So actually the RISC-V, this is called the SB format. So when this conditional branch instructions have two source registers here, and then this is the OP code, and then also function 3 field is here. And then the immediate values are assigned to the remaining field. Okay, so actually here is the RD location, but the BQ does not have any destination register, so the immediate values are occupying these 7 bits and this 5 bits. So with this conditional branch instructions, we can handle 12-bit immediate data. Okay, but it's the assignment of this immediate number is a little bit different. So actually the RISC-V so actually this conditional branch instruction just handles the immediate 12 to 1. Okay, so it's different because when the add-I immediate instructions are executed, then this add immediate instructions just handles the immediate 11 to 0. So why? So because so actually when the target address of the branch instruction is calculated, then this target address is computed like this equation. So target of the branch instruction is the current piece. The piece is the piece of current branch instruction, like BQ here. And then the immediate multiplied by 2 is added to the current piece, and then calculate the target address of this branch instruction. Target is a label. So when the branch instruction is executed, this label can be it's a 4. And then let us assume that the PC of this branch instruction is 0.04 for simplicity. So how can we calculate the target of this branch instruction? It's just 4 this the current piece and then plus 4 multiplied by 2, so it's 12. So when the condition of this branch instruction is true, then PC will be updated by 12. So that means that this program jumps to the PC address 12. So this immediate value just represent this multiplied by 2. Okay. So these 12-bit immediate values are assigned to the field of the SB format like this. So as you can see, the LSB is the 1. So that means that represents the multiply by 2 in the branch as conditional branch instruction. Okay. Okay, jump address. So jump, if you see the jump address just requires the 1 destination register and 20-bit immediate value. So this is called the UJ format. When the jump instruction is required, executed, then we just use the PC is the target of the jump instruction is just contains the PC of the target point. Okay. But as you can see, this is the 20-bit immediate value, but you can see that, oh, this immediate value is the 20 to 1. So that means that when this jump instruction is executed like x1, like 16, then this is the target of the jump instruction. Then we just, when this jump instruction is executed, then the PC, the next PC will be, it's the 32, because it's we need to multiply 2 for this immediate value. And it's because it's the same. So in the SB format, we use the 12-bit immediate value, but as you can see, the bit format of this immediate value is the 12 to 1. So we just need to multiply 2 for this immediate value. And it's same to the JAL. So we also need to multiply 2 for this immediate value, because the immediate format of this jump and ring is 22, 1. Okay. Okay. So the long jump, like it's a very long jump, and then we may need the 32-bit absolute address. Then we can use for this jump, we can use the LUI also. Okay. So if by combining LUI and JALR, then we can implement the very long jump. Okay. So this slide summarized the RISC-V addressing mode. So that means that how the RISC-V instructions handle the operands. Okay. The first type operand is the immediate operand, like this immediate field. So that means that the immediate values are included in the instruction code, and then these immediate values are directly used. And then register addressing. The data is stored in the register file, and then the instruction just point the register number, like here. Oh, no. It's a register number. And then with this register number, the register is pointed, and then this instruction uses the data inside of a target register file. Okay, this is a register addressing, and it's a base addressing. So memory instructions such as load double word or store double word, like load instruction or store instruction, use the base addressing. So with this immediate value, and then the data inside of a source register is added, and then the target memory address is computed. Oh, this is the base addressing. So with the RS register number, so the register data is pointed by this register number, and then with this register number is added by immediate value. So this is the base addressing, and PC relative addressing. Jump instruction, the conditional jump instructions use this addressing. Conditional jump used also 12-bit immediate values, like here. And then these 12-bit immediate values are added to the current PC. So this PC is the PC of this instruction. And then the target PC is calculated. Okay. So there are both types of addressing in the RISC-V instructions. Also, this slide also summarizes the instruction format of the RISC-V. So we already learned about the R-type instruction. R-type instruction has 3 register numbers, and the I-type has 12-bit immediate values, and S-type is the stores. And then, as you can see, the R-type instruction, the RISC-V has the arithmetic or logical instructions, and then I-type, you can use the enrolled or immediate arithmetic instructions like add I, and S-type is the store. So just the RD is replaced with the lower part of the immediate value, and the SB type is the conditional branch. So actually, in the S-type and SB type, the immediate number format is just different. Okay, the location of the the source registers are the same, and opcode function read are the same, and immediate values are actually stored in the same location. But it's different how immediate values are assigned inside of this immediate field. So just just note that in the S-type and SB type, how immediate values are stored is different. Okay. Okay. Also, there are UJ type and U type. So U type is the LUI, and then with this UJ type, you can use the jump instruction. Okay. So actually, in this course, we learned about the 6 types of RISC-V instructions. So actually, this information is required. So with this information, the instruction decoders can be designed. Okay, the software just generate like compiler just generate the machine instructions based on this RISC-V instruction formats, and the hardware. So hardware need to decode these instructions, the machine code instructions. So the hardware decoder also hardware also use the hardware decoder that represent these encoding rules. Okay, the hardware decodes the received instructions based on these rules. So if there is a bug on the software, then hardware may operate first incorrectly because the instructions are falsely decoded. Also, if the hardware decoder is incorrectly designed, then the software will not work properly. Okay, so that's why the instruction set architecture is called the interface between software and hardware. Okay. Okay, let's see how the instructions are compiled and executed in the computer systems. So we write a program with the high-level languages like C or Python. But Python or C is a different because the C is the compiled language, and then Python is the interpret language. Okay, also it's a little bit different. So C or Java, like high-level language, and then with this high-level language is compiled. So compiled means that high-level languages are translated into assembly code. So it's the instructions. So, but this assembly code instructions, so we can read this assembly code instructions because the human letters like A, B, C, D are used for this assembly codes, and then these assembly codes are translated to machine code or machine language. Machine language, not machine learning. It's a machine language. So that's how compiler works, and then how the compiler translates the high-level language code into the machine language. But so how the programs are compiled. So for example, this is the very simple hello world code. Like, so main function is, so either C. So main function is here, and then we use the print f, like hello world here. Yeah. So that's some example of code. Is hello world code. How this code is compiled. So this is the C program, and then C program, the C compiler, such as GCC. So GCC is the GNU C compiler, is frequently used in Linux operating systems. So this compiler reads our high-level language code. This is just a text code. It's a source code, and then compiler analyze our programs and then translate into the assembly code. Okay. And then usually if when the assembly code is created, then the assembly code has the extension like ASM. And then this assembly code is also translated into the machine code like the .obj file. So when the GCC is the very popular compiler, so I use the GCC here in this example. So when the GCC is used, then we know that actually the object files are generated from this source file. We cannot see ASM file. Why? Because usually the compiler does these two steps, and then the final object file is just generated. So this ASM file is just it's kind of some intermediate step, and then this result of the intermediate step is not created. It's not stored as a file. So if we use the -largest option with the GCC, then ASM file will be generated. But without this -s option, then object file is directly generated. So many compilers produce object modules directly. Okay. So this object file obj or .o is it's just a set of machine code. Okay, so we can if we open this file, then we cannot read this file because it's the machine code. And then this object file is just the machine code of our source file, like here. But what is missing in this case? In order to use printf function, we need library. Like, so actually we need to include the stand.io library here. Okay. What is the stand? Actually, also in this example, we just use the printf function, but this printf function is defined in standard.io libraries. So it's another compiled object. We just use the function defined in this library. So actually, not to use this printf function. So how the functions are executed? This is the main function, and then when the function is called, it's a printf function. Then the program jumps to the location of the printf function, and then instructions inside of this printf function is executed. So what does that mean? In order to execute this printf function, the machine code of the printf function should be included. Okay, so that is the set of instructions defined in other libraries. So these instructions should be included in the final binary code. Okay, so this process is called linking. So linking means that this is the object code of our source file, and then this is the object code of the library used by our source file. So object code of these two, our source code and libraries are merged. And then this merging processing is called linking. So and then this software is called the linker. So it's a linking. And binary file is generated. Okay. So if we do not use any options, then a.out will be generated. But we can use any name for our generated binary file actually. So after this linking, the binary file is generated. Okay, that's how compiler works. And then when our source file is compiled, then object file is just generated. And then this object file includes our machine code instructions. Also, the object file has additional information, such as the header and text segment. So text segment is just the translated instructions. It's a machine code of the instructions. Also, static data. So some data is the static data, and then this data was also stored in the memory. But in order to store this data in the memory, then also we need to generate this data and then store this data as a file. Okay. And then so this static data is also stored, and then this object file includes this static data segment. Okay, and then the location info is some location information about this object file or some program, loaded program, and then symbol table, like the definitions or external references. So if we use the definition, then this is stored as the symbol table and debug info. So sometimes we need to debug our code, and this debugging information is also included in the object file. Okay. And then how the linking is performed. So let's just merge the segment, and the linking is just means that merge the object code of our source code and then library code. So the segment is also merged, and then labels are reserved. So it's like a function. So when this printf function is executed, then this main function has the jump and link instruction, and then but this target should be the printf instructions inside of this library, the standard IO library. So actually this is different. So when this library is merged, then we need to adjust this target of the jump and link instruction. So this should be also adjusted, and then some references should be adjusted. Okay. So actually, but we did not learn about the virtual memory, so just ignore this part. And then how the programs are loaded. So when the binary codes are generated by compilers, this generated binary file is stored as, I said file, stored as a file, and then this file is stored in the storage devices such as hard disk drives or solid state drives. So, right? So this is just a file like a.out. So a.out is like other instructions or data. It's also a group of, it's a bunch of data. It's just a data. When this binary file like a.out is executed, we just click this a.out or in the Linux CLI, that we just type the a.out and then just push enter. Then that is called the execution of binary file, right? So this binary file is executed, then the data inside of this file is transferred to the memory of the computer system. Okay, so this is the computer system, like the CPU, memory, like DRAM, and then so storage, and then file is here, like a.out. But we learned that when the instruction is executed, this instruction just handles the data inside of a register file. Also, the data is transferred to the DRAM to the register file using the memory instructions. But where is the file? File is in the storage devices. And then it's also data. So when this binary file is executed, then the data inside of a binary file is moved to the memory. Okay. And then operating system just read the header of the file and then determines the segment size. It's some fixed storage space like text and static data. And then virtual address space is created. So it's not easy part. It's because we do not learn about the virtual memory, but just here. So virtual memory space is created for this process. Okay, so that means that for this each binary file, operating system create a memory space. Okay, and then this memory space is assigned to this binary file. So actually, it's process. Okay, so in this slide we learned about the layout of the memory. Actually, this is the layout of the virtual memory. So this virtual memory space is created by operating system, and the static data and text data is assigned to here. And then if this data is assigned to the virtual memory, and then this data is transferred to the main it's main memory actually. Okay, it's transferred to the main memory. So it's not easy. I understand. And then stack is also adjusted, and then when a C program is compiled, we use the main function, and then this main function is also a function, and then main function has some arguments. Here is the input of the function. So these arguments are also it's a set up in the main map. It's a virtual memory, so memory space, and then the registers are initialized. Right? So this the and then the arguments are stored in the extent, that is the argument of this main function, and then the instructions inside of the main function is executed. So it's a little bit, it's a little bit tricky. So it's not easy to understand, because with you are you're just learning about the very basic architecture of the computer system, but in order to understand these steps, so you need to understand how operating system works, or how the virtual memory works, like this, blah, blah, blah. And then we will learn about the virtual memory in this course, but also in order to understand how the processes, virtual memories are assigned in the computer system, then you need to learn the operating system course. Okay. So just remember that in order to execute the in order to execute our program, then those high-level language code should be translated into the assembly code and object code. It's the machine code. And then this object code should be merged with the object code of other libraries or other object code. And then the binary file is generated by compiler. Okay. And then if this binary file is executed, then the data inside of the binary file is moved to the main memory, and then some parameters or arguments are initialized, and then actually the data inside of this binary file, like text file or static data, is used, and then this file is executed. Okay. And sometimes you can use the dynamic linking instead of static linking. So static linking means that just this object code of the static library is merged with our source code. But if so, then the memory space can be wasted by unused functions of these libraries. So this is just a waste. So instead of this static linking, we can use the dynamic linking. So dynamic linking means that if a certain part of the library is used, that means that function is called, then this object code of this library is just transferred to the memory, and then it's used when it is called. So it's a dynamic linking. It's just somewhat, so it's very similar to the knowledge you need to learn in the operating system. Okay. Okay, let's see the effect of the compiler. So when we use the GCC, we can use the -O option. So with this -O option, we can adjust the optimization level of the GCC. So if we use the -G option, this is the not optimized compilation. And then if we use the -O1, -O2, -O3, then the optimization level 1, 2, 3 are applied to during the compiling process. Okay. So let's see the influences from compiler. Okay, so it's also very critical for the performance of programs. So let's see the relative performance. Let us assume that -G option is a non-optimized version. The performance of this non-optimized version is 1. So then performance of the O1, so optimization level 1, should be is higher than 2. It's like 2.4. It's very similar for O2 and O3 option. So when the optimization techniques are applied, then performance can be improved. Okay. So when we use the minus O1 or O2 or O3 options, then the performance is improved higher than 2. Okay, how? So let's analyze why the performance is improved. So so how can we measure the performance? We need to measure the execution time. Then how can we calculate the execution time? Execution time is the instruction count multiplied by CPI multiplied by TC, clock period. But this is the same hardware, so TC is the same. Okay, so TC, so just we can ignore the TC because TC is the same. Okay, so we can just compare the instruction count and CPI. So let's see the instruction count part. So how are the instruction count? For the non-optimized version, the instruction counts are very high, but as you can see, it's reduced. The clock cycle is just the inverse of the relative performance. How about the CPI? As you can see, CPI is increased when we use the O1 option. So what does that mean? If the instruction count is the same, and then if the CPI is high, then performance is decreased. Because if the CPI is high, then execution time is also increases. So, and then high CPI is not good for the performance usually. But when we use the optimization techniques for the for compiling, then CPI can be increased. But what is the benefit of this performance improvement? What is the reason of this performance improvement? Instruction count are decreased. So what? So even though CPI is increased, the instruction counts are dramatically decreased. So performance is improved. So that is the effect of compiler optimization. Okay. So and then so this result shows that compare the performance of two different configuration, we need to check instruction count and CPI and also the clock period based on this equation. Okay. Let's see the effect of language. So it's a programming language and algorithm. So this is the C code, the performance of the C code, and then this is the performance by Java code, and then this is the performance by Java just-in-time compiler. So actually, if we use the Java, then Java compiler just generate the byte code, and then this byte code is executed on the Java virtual machine called the JVM. So in order to execute when we use Java, then this byte, if we just has this byte code, and then this Java byte code can be executed on any platforms because of a Java virtual machine. Okay. So if you do not know about the Java, just try to search for Java on the Google. Okay. So, but let's compare the performance. If we use the Java, if we use the Java virtual machine, then the performance is dramatically decreased. So that's the problem of the Java code. But if we use the Java just-in-time compiler option, then the performance is improved. So actually, Java just-in-time compiler is very similar to the compiler of C. So program language also can affect the performance of our application. So if we use the Python, the performance will be very slow because the Python is the interpreter language. Okay, so C is very fast. If we just focus on the performance of our application, then we need to use C. But if the different algorithms are applied, then performance can be different. So if the quick sort algorithms are applied for the sorting program, then when the all three options are applied, the performance is improved dramatically. So sometimes algorithm also affect the performance by compiler options. Okay, that's why the computer systems are very difficult to understand. It's very complex. Okay, so there are many actually there are many factors to change the performance of computer systems actually. So in this example, we know that the program language also influence the performance, so the optimization option, and then the algorithm, and then also the optimization option can exhibit the divergent performance result based on the algorithm of an application. Okay, so there are many factors to influence the performance of applications. Okay. So array versus pointer. So I will skip here. So actually, okay. So we can use the array. So when it handles the array data, like A0 to A99, so this is some example of array data. So we can use the array indexed by this index number. Like, so this the number is called the index number of array. So we can use the array like this, but we can also access the element of an array using pointer. So if you know about the C program, then actually pointer is the tricky part of the C programming actually, because the pointer is just mentioned the address of variable. Okay, so instead of using index of array, then we can directly use pointer. So pointer is just address of variable. So this is the example. So in this example, we can update the element of the array with the index number here. And then in the right side program, we just directly change the pointer value, and then we just update the content of a pointer with the 0. Actually, these two programs are the same, but we can use the pointer directly, or we can use the index number for arrays. And then if these programs are directly compiled, that means it's a directly compiled. So just focus on that directly. Then the generated instructions can be different. Okay, so no compiler optimization is applied. Okay, so what is different? So in this loop, there are 5 instructions here, and then as you can see in this loop, there are 3 instructions. Okay. Oh, you may think that number of total instructions are the same. 1, 2, 3, 4. Oh, there are 6 instructions. Oh, this, oh, 1, 2, 3, 4. It's a 6 instructions also. So you may think that, oh, this program has 6 instructions, and then this program has 6 instructions. The instruction count is the same. So if the CPI is the same, then performance of these two code, performance of the two codes will be the same. That's right. No, right? Yeah, you are right. It's not true because you need to focus on the number of instructions inside of this loop. So let us assume that this loop is executed 100 times. Okay, 100 times. So what is the total executed instruction for this code? It's 1 plus 100 multiplied 5. It's a How about this code? It's a 3 plus 3 multiplied by 100. It's about 300. It's a 500. If the array size is very large, and then because of differences in the number of instructions under this loop, the total executed instructions can be different. Which code is better? This code is better. Why? In order to calculate the index, so we just increase the index number with I, but in order to calculate the actual address of each element, we need to calculate like this. We need to calculate the offset like this, I multiplied by 8. But if we use just the pointer, then we can just directly increase the pointer number. So that is, pointer is just address. So in this example, this code is included inside of the loop, and then but this code, this part is not included in the loop. That's why the total number of instructions can be different. So execution time is very important. I see CPI T. So if we can reduce this instruction count, then we can increase the performance. But don't worry about this. Compilers are very intelligent. This is very smart. So compilers can generate the same code, even though we use index style programming. Okay. So we don't need to worry about this case. Okay. Can use the index more conveniently, index type. Okay, so I tried to cover the x86 instructions, but we don't have enough time. So just to read these slides. So actually in this course, we do not cover the x86 instructions because x86 instructions are CISC type ISA. It's complex. But RISC is much simpler than CISC. So we do not cover the x86 instructions, but x86 instructions are very popular. So actually the x86 instructions are developed by Intel. The Intel is the biggest CPU vendor. So that means that the x86 is the most popular ISA in the computer systems, but it's very complex. Also, it is commercial ISA. Okay, so you can just read these slides right here. So you can find the history of the x86 ISA, but you can find that new instructions are included every generation, like MMX, some SSC2, like these new instructions are included continuously. So that's why the CISC is the x86 is also very complex, and then the number of instructions are very large. The x86. Okay, so address register also x86 support the very complicated addressing mode. It's different. Okay. So okay, so I will conclude the chapter 2 so this today, and then so do you have any questions? Midterm one. So actually I post the logistics of the midterm exam on Blackboard. Okay, so we will take the online exam using a lockdown browser and Zoom. Okay, then this online exam will be open book exam. And then I plan to take the so we will take the midterm exam during regular class time. Maybe it's Monday. It's a Monday. I think it's Monday, like November 2nd. I don't remember the exact day. So please, I already post. So I post the logistics of this midterm exam on the Blackboard. Okay. Okay. Thank you for your attention, and so I will record the next class, and then I will post the recorded video until Friday, because we missed the Monday class, but we need to have the regular number of classes. Okay. 네, 그렇습니다. textbook slide, you can see your material, textbook, some papers, anything during the exam, but you cannot access internet, you cannot access your smartphone, you cannot use your computer. Actually, if we use the lockdown browser, November 2nd is maybe Monday? 11월 2, I think it's November 2nd. No. November 1st. Yeah, November 1st is Monday. So maybe we'll take the midterm exam on November 1st. Okay. Okay, bye. See you.